In this next presentation, we're going to look at VLANs and VLAN trunking protocol. This is one of the more important presentations, so I want you guys to have a keen understanding of what VLANs are, how they're implemented, and some of the advantages and disadvantages of VLAN trunking protocol. So now we move from the problem of collision domains to the problems associated with broadcast domains. Now that we've solved all the problems with collisions, it would be nice to be able to segment broadcast domains as well. This could be for security. For example, you may not want the business department accessing the engineering department's servers. This is also for increased bandwidth. For example, let's look at the graphic arts school. The graphic arts school may need a lot of bandwidth specifically for uploading and downloading videos to or from their servers. If they're using all of this bandwidth, or if they're using broadcasts for various resources, it would be very, very nice to not have to worry about that interfering with other university operations, and so putting them on their own broadcast domain would be better. Obviously, for better organization, separate LANs for separate departments would be nice, as I mentioned in my previous example. And overall, there are certain situations where it would just make sense to have different devices on different broadcast domains. So now we need to figure out a way to divide broadcast domains, and that is effectively what VLANs do. So the solution to this problem of segmenting broadcast domains lies with VLANs. VLANs allow several different LANs on a single switch, so I can segregate, say on a 24-port switch, I can put the first 8 ports into VLAN 1, the second 8 ports into VLAN 2, and the last 8 ports into VLAN 3. And the ports on VLAN 1 would not be able to talk to any devices on VLANs 2 or 3, and the same goes for, VLANs 2 or 3. The idea here is that each VLAN is a separate broadcast domain. And the really cool parts about VLANs comes into this next bullet point. We can actually extend a VLAN from one switch to another. We do this with what are called trunk links. And so if we wanted to, we could have VLAN 1 on one switch and VLAN 1 on another switch. And VLAN 1 on both of these switches would be in the same broadcast domain. That is, devices on that VLAN would be able to interact with each other and would be separate from VLAN 2. And we could do the same thing with other VLANs. VLAN 2 may extend between 2 or 3 or more switches using a trunk link. And there are 2 different ways we can do VLAN tagging on the trunk. I'll talk more about what VLAN tagging is and how it works in a moment and later on in the presentation. But there are 2 methods for tagging that you need to know about. The first one is what is known as interswitch link. This was a Cisco proprietary method. ISL encapsulation is actually depreciated and it isn't even available as an option on most modern iOSs. Another option that's more standard now is 802.1q trunking. This is again the IEEE standard. There's much less overhead, and it has basically become the standard, and it's inter-vendor compatible, so you don't have to worry about it not working with certain switches. Hosts on the same VLAN can communicate, and hosts on different VLANs would require a router to communicate. We are not going to talk about routers just yet, and so in this example you can safely assume that devices on different VLANs cannot communicate. I want you to visualize these VLANs with the following diagram, and I want you to go ahead and pause it after I finish talking about this so you really get an idea of what these VLANs mean. You'll see that there are 2 switches here, and you can tell this is kind of an old diagram because it uses an ISL encapsulation between the 2 switches, right? You can ignore the Cisco iOS routers and that HSRP cloud up there. Basically the idea here is that we have 2 switches, and I see VLAN 10, I see VLAN 20, VLAN 30, and if you look on the switch on the right, there's a VLAN 40 down there. Now the idea here is this. You'll notice that there are 2 computers in VLAN 10 on the switch to the left, and another 2 computers in VLAN 10 on the switch to the right. All 4 of these computers are considered to be in the same broadcast domain, and that ISL trunk between the 2 switches will pass traffic for VLAN 10. Now the ISL trunk will keep separate the traffic from VLAN 20, and you'll notice that there are 2 VLAN 20 computers on each side of this inner switch link trunk as well. Now you'll notice on the left there we have VLAN 30, and on the right we have VLAN 40. Now these VLANs are independent of each other and independent of the VLANs that we've discussed so far. So all devices in VLAN 10 are on the same broadcast domain. All devices in VLAN 20, 30, and 40 are on their respective broadcast domains. And so basically we have the ability to, one, separate a single switch into several broadcast domains, and two, extend those broadcast domains across multiple switches. So VLANs provide a very useful tool for network engineers. Now I'm going to get into a little bit more about VLAN tagging. So there has to be some sort of mechanism when we're passing traffic from several VLANs across a single link. We have to be able to distinguish traffic from one VLAN from traffic from another VLAN. And an 802.1q, this is done with what's called an 802.1q VLAN tag. This VLAN tag is comprised of several different fields. The last one you can see there on that lower portion on the right is the VLAN ID. This VLAN ID is one of a possible 12-bit ID. These go up to 4096. That is the highest possible VLAN ID. And so you'll notice that this .1q tag is inserted after the destination and source MAC address. It's just kind of stuck in there. There's not really a header or footer. It's just kind of added, and that's why it's referred to as a tag. And so devices that are on a VLAN, when the switch sends that data over a trunk link to segregate it from the other data from the other VLANs, it will place a VLAN tag on that particular data with the correct VLAN information. And the device on the other end will receive that, note the VLAN tag, and basically forward it onto the correct VLAN and possibly the correct device. Now we run into a new problem of configuring VLANs on several switches could take a while. Basically, we need to configure every single VLAN on every single switch. I'll note at this point that by default on Cisco switches there is only one VLAN, and that is VLAN 1. So what we need to do to add a new VLAN, we have to add that VLAN on every single switch that needs to pass that VLAN's traffic. For example, suppose I have 3 switches and I want to configure VLAN 2, and I want a few devices. These switches are connected in a linear style, so I'll connect 1 to 2 and then 2 to 3. I have some VLAN 2 ports on the first switch and some VLAN 2 ports on the third switch. The second switch actually does not have any VLAN 2 ports, but it still needs to pass VLAN 2 traffic. And so what I will have to do is I will have to create VLAN 2 on all 3 switches. This can become quite a pain for network engineers, and so we need a way to be able to easily add VLANs. You can imagine some enterprise networks become, several hundred switches big, and I don't know if you would ever imagine trying to configure VLANs on all 100 switches. It would take forever. So we want an easy way to push VLAN information between these switches. We do that with VLAN trunking protocol. VLAN trunking protocol is basically designed to allow a single switch to push this VLAN information to a surrounding switch. This VLAN information is contained in what we call a VLAN database file. And this VLAN database file, typically on switches, it is denoted VLAN.dat as the file name, is pushed to other switches surrounding it. So a switch can be in one of 3 VTP modes. If the VTP mode is server, then this device can send and receive information from the switches surrounding it. If the device is in client mode, the device can receive VLAN information but cannot send it. In other words, you will receive new VLANs, but you cannot actually make any VLAN modifications on this particular switch. A device can also be running in transparent mode, and when the device runs in transparent mode, it will just pass the VTP information through. It won't actually take it and use it in any way. This basically eliminates the need for switch-by-switch configuration because VLAN information can be pushed from a server to clients or to other servers. So here's a very, very simple VTP diagram where we have a VTP server pushing VLAN information to 2 VTP clients. You'll notice that this brings in a new concept called revision number. And so when a new VLAN is added, or when the VLAN database is changed, the revision number on that switch is incremented. And the idea behind VTP, the basic algorithm is the higher revision is the ruling revision. So as you make a new change, it increments the revision number, and other switches will see that new revision with a higher revision number, and will take it and install it, and basically just take its word as law. Every time the VLAN database is updated, this number is incremented. Again, you saw that in the diagram just now. VTP clients and servers will all check whether the version they receive is higher than the currently installed version. I bet you can imagine this will cause problems with different VTP migrations. For example, suppose I have a switch that has a VLAN database with revision 15, and I plug it into a brand new network that I've just freshly configured VTP on. The revision may be, say, 3. The old VLAN database that has revision 15 will, if VTP is configured the same on all devices, overwrite the newer VLAN databases on the newly configured VTP switches, just simply because the revision's higher. The revision is all that matters. Now, there are ways in the switch to configure the VTP revision number. We may talk about those in the next module. You can have more than one VTP server in a network, and this is one of the interesting applications. Say I have a network with 5 switches. I could make all 5 switches, VTP servers, and what will happen is if I make a change on one switch, it will increment the revision number, and all the other switches will look at that new revision number and accept it because the new revision number is higher. And this could be done on any switch in the network. There are 3 versions of VTP. Basically, what you need to know is that version 1 does not support any sort of secure authentication. Version 2 supports some basic authentication. There's a version 3 that runs on higher level switches that you will probably never encounter. Version 2 is the most common version out there. This ends the presentation on VLANs and VTP. Obviously, there's a lot of information here, so I encourage you to review this presentation and review the corresponding textbook chapters. If you have any questions, please let me know. Leave comments, please feel free to rate this video, and I hope you enjoy, and I'll see you in the next presentation.